1. Okay, now we're going to discuss forces on a flat surface, and more particularly, we're looking at pulling forces. In other words, you have a 25 kilogram crate on the floor, and it's there's no incline, so it means it's a flat surface, the floor, it's ground, whatever. And you want to move the crate, so you shove it forward, push it. So how many forces are working on the crate? Well, the fact that you get it to move means that there are forces in total that are unbalanced. Okay, remember Newton's first law, which states that an object at rest will stay at rest unless an unbalanced force is applied. Well, that crate's sitting there, and all of a sudden you come along and shove it, it's now an unbalanced force. So, how many forces are working on the crate? Well, the fact that you get it to move means that you can push it forward, so that is one force. But the question is there something working against it that causes it to be an inertia? And the answer is yeah, there is. And that's called friction. We'll get into friction later on, but that's a force that's working against it. The fact that we're able to get it to move means you've overcome the friction, so there's your unbalanced force. You have more push than the push back against you by the contacted surfaces between the crate and the floor. That's called friction. What else is working on it? Well, you got gravity working down on it, trying to pull it towards the center of the earth. Okay? But something has to be balancing that to keep it from going through, and that is the floor pushing back up. So those two forces are equal because there's no movement up or down. So those are balanced forces there. But the unbalanced force is you pushing, friction pushing back against you, but you have a stronger force forward than it does backward, or stopping. Alright, so that push forward we call a horizontal force. Very similar to what we talked about with the vectors, where you had two different vectors that you could figure out from an oblique vector. Same thing works with forces. And we can do the same kind of thing with forces that we did with velocities in dealing with vectors. So if we think in terms of vectors, we had a forward vector, a backward vector, and the difference between the two was the unbalanced force that was happening. So let's forget friction now. Like I said, we're going to talk about friction. And if we're going to forget about friction, we're going to just assume that all we have to do is just make the most minute of shoves and get it to move. Now, most people, when they deal with a crate, go like bending over and doing this if they can avoid it. So a lot of times they'll attach something like a rope or a string to it, depending on how heavy it is, and just kind of drag it along. Just kind of the crate falling along. It's like a little puppy dog that doesn't want to move. Alright? So now you're dragging it at an oblique angle. Instead of straight across at 0 degrees, it's now up. In this particular case, let's say we're going to make a 30-degree angle with the floor. So if we have a crate that looks something like this, and you attach some kind of rope to it somehow, and that rope is parallel to the ground, and that rope there makes a 30-degree angle, that's what we're looking at. And just like the vectors we dealt with in the last chapter, we dealt with velocity, we can find components, horizontal components and a vertical component. So let's see what they're telling us here. Okay, let's say it takes 50 newtons, you take 50 newtons of work, or force rather, to drag this along. So that means our applied force is 50 newtons. So FA equals 50 newtons. Well, this is our vertical force here. This is our horizontal force right here. Vertical force, then, is the opposite, using SOHCAHTOA here, the opposite over the hypotenuse, and that is SOH, S-O-H. So that means then that if we use the formula, sine of 30 degrees equals opposite, which is F sub V, over hypotenuse, which is 50 newtons. Then get F sub V by itself and multiply both sides by that 50 newtons. that means that F sub V is equal to 50 newtons times the sine of 30 degrees. And it turns out that that is 25 newtons, because the sine of 30 degrees is 1/2. Now we go to the horizontal force here, and that is the adjacent side to that right triangle that's been created. So we're going to be looking at adjacent over hypotenuse. So TOA. So cosine of 30 degrees equals F sub V over 50 newtons. And so we multiply both sides by 50 newtons again, like we did over here. And F sub V becomes 50 newtons times the cosine of 30 degrees. I don't remember offhand what that is, so let's cheat a little, take a look at that answer. 43.3 newtons is what that turns out to be. And that's all there is to that. All right? So let's take a look at another example here. Kind of reinforce that. Well, actually, no, we're going to talk some more about that, the implications behind that. And what's important about that particular scenario that we'll get into when we talk about friction is what we call a normal force. The downward force is the weight. The weight is the force of gravity. It's pushing perpendicular right into the surface. Okay? But because it is perpendicular, it is also called a normal force. So the weight is perpendicular to the surface, and by definition, a surface perpendicular to the surface simply means that it's a normal force. So that force, the weight, is found by taking m times g, which is 490 newtons here. Okay? So let's put that in there. The weight, F sub W, weight is a force, and we know that the formula for force is m times a, but because this is weight, this is gravity right here, we're going to turn that into g. And so this becomes, let's see, how big was the, let's say 25 kilogram case, so 25 kilograms times 9.80 meters per second squared, and that gives us 245 newtons. So the force straight down into the ground is 245 newtons. Now, before we lifted, that was also equal to the normal force. But, and there's always that big but, when you lift up, you're taking some of the gravitational force off the ground. You're bringing it up and you're pushing it forward. So that bringing up decreases the normal force because you've lifted up from it.